In this video, we investigate random variables. We learn how mathematicians define random variables, and we learn about some of the key mathematical objects that are associated with them. A random variable is a function. It's a function that maps outcomes from the sample space omega to real numbers. It's common to use capital X to denote this function. As an example, consider the experiment in which we flip a coin. In this case, we could define the random variable capital X as the function that maps the outcome heads to the real number 0, and maps the outcome tails to the real number 100. Random variables have another important feature that often goes unrecognized by students, possibly because it makes intuitive sense. That feature is this. When presented with any interval of the real line, we can always trace the numbers mapped here by capital X back to an event in omega. We might describe this event as capital E, or as the event that capital X lies between A and B. This feature of random variables is important because it allows us to port our discussions of probability from previous videos over to our future discussions of random variables. Probability theory pays particular attention to the event that capital X falls in the interval from -infinity to some particular number denoted here as lowercase x. The probability of this event is treated as a function of lowercase x and is termed the cumulative distribution function. To see an example, let's consider a fair coin, and we'll again use the random variable capital X that maps heads to 0 and tails to 100. When we sketch the cumulative distribution function, it looks like this. It sticks to a height of 0 for negative values of lowercase x, since there's no chance that capital X takes a value less than 0. When we hit 0, though, the function immediately jumps to a value of 1/2. That's because the probability that capital X is less than or equal to 0 is the probability that we observe heads. The function continues at a height of 1/2 for a while until we hit 100. Here we get a second jump. When lowercase x hits 100, the function takes on a value of 1. That's because we are guaranteed at this point that capital X is less than or equal to 100. Of course, beyond 100, the function stays at a height of 1. We're also guaranteed that capital X is less than or equal to any real number that exceeds 100. This sketch illustrates the general properties of cumulative distribution functions. The limit as lowercase x goes to -infinity of the cumulative distribution function is 0, and the limit as lowercase x goes to +infinity of the cumulative distribution function is 1. The cumulative distribution function is also non-decreasing and is right continuous. In order to make progress at this point in our discussion, we'll need to put random variables into one of two basic categories. Our first category will be discrete random variables. In this category, we put any random variable, capital X, whose range consists of a discrete set of numbers, say lowercase x1, lowercase x2, and so on. I'll emphasize that the discrete set of numbers may be finite, but there are also cases in which it's infinite. Now, consider Ej defined as the event we observe an outcome that our discrete random variable, capital X, maps to the number lowercase xj. We'll use Ej to define a new function, lowercase p of xj. This function is equal to the probability of the event Ej, or simply, the probability of the event that capital X is equal to lowercase xj. We call lowercase p the probability mass function. To see what this function looks like for a particular experiment, let's again turn to our fair coin and the random variable capital X that we've already introduced. Let's now sketch out the graph of lowercase p. The graph follows the horizontal axis here because there's 0 chance that we observe a value of lowercase x that's negative. That changes when we hit lowercase x is equal to 0. Here, the function pops up to a value of 1/2 because that's the probability of observing heads. and it's heads that maps to 0. Once we've passed 0, the graph drops back down to the axis, because we're in a region where lowercase x values are impossible. We stay here until lowercase x is equal to 100, at which point the graph pops up to 1/2 again, because that's the probability of observing tails, and it's tails that maps to 100. Once we're past 100, the function drops back to the axis yet again and stays there as lowercase x increases further. For discrete random variables, we can establish a connection between the probability mass function and the cumulative distribution function. The connection is easily explained with a picture. Here on the left, we have the probability mass function we just constructed. On the right, we have the corresponding cumulative distribution function constructed earlier in the video. If you stare at these pictures side by side long enough, you notice that we can lift the 1 on the left in a particular way to get the 1 on the right. By this I mean we can raise this bit to here, and this bit to here. Using some technical notation, we can describe what we've just done as follows. The cumulative distribution function, evaluated at some lowercase x value, is equal to the sum from j equals 1 to n of the probability mass function at lowercase xj, when the lowercase x is no less than x sub n, but is strictly less than x sub n plus 1. The second of our two categories of random variables is termed continuous random variables. A continuous random variable is one for which there exists a non-negative function, say lowercase f of x, such that for any interval capital I, the probability that the random variable capital X is found there can be determined by integrating lowercase f over said interval. In addition to lowercase f being non-negative, we require that its total integral over all real numbers is equal to 1. The function lowercase f is called a probability density function. Here's an example. A function whose graph resembles an isosceles triangle. Clearly, the function is non-negative. Its graph never dips below the horizontal axis. It also satisfies our second criterion, since the total area under the curve is equal to 1. To see this, just recall the formula for the area of a triangle. It's important to remember that for continuous random variables, probabilities are not given by the height of the graph. Instead, as we said a moment ago, probabilities are the result of integration. If we wanted to find the probability that capital X is found on the interval from -1/2 to 0, for example, we would integrate from -1/2 to 0. The area under the curve on this interval is 1/2, which gives us the probability we're after. For continuous random variables, the connection between the cumulative distribution function and the probability density function is established by this equation. Recall that capital F, here evaluated at A, is meant to express the probability that our random variable is less than or equal to A. As we've just seen, this probability can be calculated by integrating the probability density function from -∞ to A. If putting -∞ as a limit of integration seems strange or unfamiliar to you, just think of it as a limit of definite integrals, and work on the assumption that the limit of definite integrals exists. If the probability density function is continuous on the interval from -∞ to some point beyond A, and if we apply the fundamental theorem of calculus to this weird-looking integral in the same way we did to definite integrals, we arrive here. This says that the probability density function is the derivative of the cumulative distribution function. This also gives us a differential equation we can use to construct the cumulative distribution function when presented with only a probability density. Here's an example of what I mean. Take the probability density function we studied just a moment ago. Clearly, for values of lowercase x less than -1/2, the cumulative density function is 0. Things become more interesting on the interval from -0.5 to 0. Here, the density function is a line of slope 4 with vertical intercept 2. This means the differential equation we want to study is this, to which we attach the condition f at 0 is equal to 1/2, since we just calculated that a second ago. We can easily solve this initial value problem to find this. Something similar happens on the interval from 0 to 1/2, but here the density function has slope -4 with vertical intercept 2. So now the initial value problem is this, which we solve to get this. Beyond lowercase x is equal to 1/2, the density function is 0, which means that the cumulative distribution function does not change in value. It remains forever fixed at the same height it achieved when x was equal to 1/2. For the sake of completeness, I'll spell out the result of our discussion here. We can plot this function as follows. Again, we see that the cumulative distribution function is non-decreasing and is right continuous. In this case, it's actually continuous. In this specific instance, you can also see that the graph of the cumulative distribution function looks like an amalgam of the quadratic expressions, basically parabolas, that arose as solutions to the initial value problems we solved a moment ago. Let's recap. In this video, we defined a random variable to be a function that turns outcomes from the sample space into real numbers. We defined the cumulative distribution function and laid out its various properties. We talked about discrete random variables, introduced the probability mass function for a discrete random variable, and we established a connection between the probability mass function and the cumulative distribution function. We did pretty much the same thing for continuous random variables, though in this case our discussion surrounded the probability density function. Once you've come to terms with the ideas presented in this video, you should be able to do the following. You should be able to explain what a random variable is, and you should be able to contrast discrete random variables against continuous ones. You should be able to define the cumulative distribution function, probability mass function, and probability density function. And you should be able to construct each of these when given the right amount of information. You should be able to explain the connections between the cumulative distribution function and the probability mass function and density function, respectively. Finally, you should be able to use all of these functions to determine the probability that a random variable takes on a given value or values. In closing, I'll say yet again that success in this course can't be achieved by only watching videos. Videos are just the beginning. Make sure you read the notes and try the problems. Also, don't be afraid to lean on resources that you find yourself, like books from the library. Getting different perspectives on the same topic is a great way to grow as a mathematician and as a scientist.